Okay, so this is notes for 7.5, graphing exponential growth functions. So from left to right, we are going to be growing on an XY plane. We're actually going to be graphing exponential growth functions. Before we begin this, let's actually take a look at an opener here. So here's a situation, hypothetical situation. Make believe. We're going to pretend that this is happening. You're going to talk to a partner and make the best decision. So here it is. If a mysterious man comes up to you on the last day of school and says, I need you to wash cars every single day for 30 days straight during the summer. I'll pay you good money. So you ask him, how much? He responds, whatever you want. And then you say, how about $1 million? $1 million. So he stops and thinks and says, sure, I can give you the million, but how about instead of $1 million, I give you a penny right now. And then on the first day of work, I'll double it and give you 2 cents. Then the second day of work, I'll double it and that'll be 4 cents that I'll give you. And then we'll keep doubling and so on, right? For 30 days straight. So what do you think? Would you like to take the $1 million up front or take a penny right there?
A penny. And
then on the first day, you double it.
How much would you have by the end of the...
Well, that's a question. I want you to think about the math. I want to give you guys a good 2-3 minutes to talk about it with a partner. You might want to start jotting down some numbers on a piece of paper. And I want you to give me a good reason why you would pick what you pick, either the $1 million or the penny doubling as we go. I'm going to pause it. Go for it. Talk about it. How many people say they would take the $1 million up front? Instant millionaire. A lot of you guys? And some of you are saying chale? Okay. How many would take the pennies doubling each day? Okay. And I guess the rest of you don't want to work and make any money, right? Because some of you didn't vote. Okay, so check this out. I actually have it shown right here that, yeah, day 0, the guy says, here, take this penny. And on the first day of work, I'll double it and give you 2 cents. Second day of work, I'll double it and give you 4 cents. Third day of work, and so on and so on. So let me do this. I want to just scroll and see day 6. By day 7, you've been working 7 days, and for the whole 7th day of work, he gives you $1.28 on the 7th day of work. That's pretty horrible, right? That's 1 week already. And it's only a month that we're doing it. But then again, if you continue, day 8, $2.56, day 9, $5.12, day 10, let's go to the second week. Let me see. By day 14, even though it's the 14th day, 2 weeks of work, he pays you $163 for the whole day. That's not bad, $163 for a day. Now, if you keep doubling, 15, 16, 17, day 18, day 19, by day 20, you're already making $10,000 for that 20th day of work. 21st day of work, $20,000. Now look, by the 27th day, for 1 day of work on the 27th day, you're making over $1 million on the 27th day. If you keep doubling, on the 30th day, you make over $10 million. So if you chose, and not only that, it's not like, oh, I missed out on 10 million. No, you got to add it all up, right? So if you pick the million, that's like the biggest mistake of your life. So if a man ever does ask you, pick the penny, doubling each day, okay? So the reason why I'm showing you this is because this is actual exponential growth. At the beginning, the first couple of days, it seems like it's not growing that fast, like it's not worth it. But all of a sudden, it grows a lot, right? It grows a lot. That's what exponential growth is. Let's take a look at some notes. The learning target is at the top of your notes. It's also on the board right there. It says, by the end of this period, I'll be able to graph exponential growth functions, state the domain and range, the y-intercept, and the asymptote of any exponential growth function. So we have a lot of vocabulary right here that we need to get comfortable with, that we should remember from semester 1. Remember, domain, simply all your x values, the input values, all your x values of whatever function you have. The range is all your y values, the output values, all the y values of whatever function you have. Parent graph, this sounds confusing. It's the function without a, h, or k, but we'll get to that later. Parent graphs are just the way the other graphs look, right? So it's kind of like, they call it parent graph because if you see my son, you're going to be like, hey, he looks like you. Yeah, it's because I'm his parent, right? It'd be weird if He wouldn't look like me. Anyways, so a parent graph, we'll get to that in a little while. Also translation, the word translation, that's really a shift. It could be a left or right shift. It could be an up or down shift. And right here it says according to H and K, including the A value. It'll make more sense once we actually get to some problems. The y-intercept, we already know what a y-intercept is. It's where your line or your graph crosses the y-axis. How do you find that point? You set x equal to 0, which means you plug in 0 for x and you solve for y. And that'll tell you exactly where it crosses the y-axis. Now, the word asymptote, do not pronounce it asymptote, right? It's asymptote. And asymptote is the line that your graph will infinitely approach but never actually touch. I know that sounds weird, but I'll show you some examples in a bit. So the line y equals k is going to be our equation for the asymptote on this particular section. Like I said, these notes, you're going to be able to go back and read it. It'll make more sense once we go through some examples. Now here's the form that we need to get comfortable with. Y equals a times b to the power of x minus h plus k. Now this is going to be used a lot in Algebra 2. In Algebra 1, we're not going to be really using the h value on our homework or on the quiz or test, but we will be using a k value. Like I said, we'll understand all this in a little bit. But right now let's start understanding what an exponential growth function looks like by actually graphing the most basic type of exponential growth function, y equals 2 to the x. Now the previous example, that hypothetical situation of you having 2 cents on your first day of work and then doubling it 4 cents and then doubling it 8 cents, that's actually represented with this exponential growth function. So what I want to do to graph is how we graphed when we first started graphing lines. Let's make an XY table. And what I want you to do is to plug in consecutive integer inputs. Very nice numbers that are in order. So let's start with like -3, -2, -1, 0, 1, 2, 3. Now this very first example that we're doing, it's going to be a very long process. We're going to do a lot of math. But as you see, as we go on from example to example, we're going to come up with certain shortcuts that make it a lot faster, okay? So anyway, let's start with the easiest number to plug in, which would be 0. So I want to put 0 for my input right here. What's 2 to the 0 power? 2 to the 0 power, remember from exponents, anything to the 0 power equals 1, right? So 2 to the 0 power is 1. So for my input 0, my output is 1, and that's a coordinate. Let me actually graph that coordinate. 0, 1 is right there. And I hope you guys are following along on your handout. Now let me plug in the number 1. I'm going to take the number 1 and plug it in right there. What's 2 to the 1 power? What's 2 to the 1 power? That's 2, right? And that's the next coordinate, 1, 2. So if I were at the origin and I go 1 on the x, 2 on the y, I'll end up right there. So let's all put a dot right there. And let me plug in the next input, 2. If I plug in 2 right in there, what's 2 to the second? 4. And that's our next coordinate, 2, 4. So once again, here's the origin. 2 on the x, 4 on the y would be right here. Let's put a dot right there at the coordinate 2, 4. And last but not least, 3. Plug in 3. That's going to be 2 to the third. Is that 6? Yeah. No. What's 2 to the third? 8. 2 times 2 times 2 is 8. So there's your coordinate 3, 8. So let's actually graph that coordinate by going, here's the origin, going 3 on the x, 8 on the y. It'd be way up here, put a dot right there. Now, if I did go to the next input 4, what would the output be? What's 4 squared? What's 4 squared? I mean, 2, what's 4 squared? What's 2 to the 4th? 16, right? So if I did go 4 on the x and 16 on the y, I'd be off the graph, so I'm not going to use that coordinate. Is everybody with me so far? Okay. So what about these negative inputs? What if I plugged in a -1? If I plug in a -1, this is where it gets a little more interesting, because if I go 2 to the -1 power, you guys remember rules of exponents? Anything to a negative power, you must get it, move it to the other side of the fraction, and it'll become positive. So I need to first make it look like a fraction, and then grab it, move it to the other side, and it'll become what? 1 over 2. So for the input -1, I get the output 1/2. Are you with me? For the input of -2, what's 2 to the -2? You move it down and it becomes 1/4. That's right, 1/4. And how about for the input -3? 2 to the -3, what do I get? 1/8. That's right. Now, let me tell you this, guys. When we are organized with this XY table and we use consecutive integer inputs, numbers that are in order, -3, -2, -1, 0, 1, 2, 3, 4, when they're in order like that, we will be able to see patterns and use the patterns. Okay? So what pattern do you see from 1 to 2, from 2 to 4, from 4 to 8? How do you get from 1 to 2? Doubles, and then it doubles, and then it doubles. It's multiplying by 2, right? Yeah. So as you're going down, 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16. Going backwards would be doing what? Dividing by 2. 16 divided by 2 is 8, divided by 2 is 4, divided by 2 is 2, divided by 2 is 1, divided by 2 is half, and then divided by 2 is 1/4, and divided by 2 is 1/8. And it keeps getting smaller and smaller and smaller, but will it ever actually get to 0? No, it'll never actually get to 0. So let me actually start graphing some of these. So let me put the coordinate -1, 2. Let me do it in blue to keep it consistent. -1 on the x, no, half. I'm sorry, -1/2. So here's the origin, -1 and then halfway up. And the next one is -2 and 1/4. So if I go -2 and 1/4, that's 1/4 of the way up. That's technically half of the half. So that would be right here. And then half of that would be 1/8. Half of that would be 1/16. Half of that would be 1/32, and then 1/64, and then 1/128, and so on and so on. Now, to the naked eye, it looks like it actually touches the x-axis. But it never actually touches. It just infinitely approaches. So, ladies and gentlemen, this is my graph. Let me try to keep the dots in blue. And this is my exponential growth function. From left to right, it really does grow. And from right to left, it shrinks, but it never actually touches the x-axis, but it does infinitely approach. So let me give you an example right now in class of how you could infinitely approach something but never actually touch something. So, okay, so here's an example of an asymptote. Okay, so I wanna take 4 steps towards that wall. Okay, so watch my feet. Check it out. 1, 2, 3, 4, and then I'm gonna take half of that, right? Which is 1, 2. And then I'm gonna take half of that, which is 1. And then I'm going to take half of that, which is what? Half. And then half of the half, and then half of the half, and then half of the half, and then half of the half. Next thing you know, I'm just doing this. Right? I will never hit that wall. You won't. No, never. You'll never hit the wall. It's kind of, I mean, think about this. If you get a calculator and you did. Exactly, but
it'll take like a really long ass time.
No, it'll infinitely approach but never touch. Now let me prove it to you like with a calculator if you want. If you get a calculator and you divide 8 divided by 2, what are you going to get? 4. And then divided by 2, what are you going to get? 2. And then divided by 2, what are you going to get? 1. Divided by 2, you're going to get 0.5. And divided by 2, you're going to get 0.25. Divided by 2, you're going to get, so it keeps getting smaller and smaller, but it'll never actually get to 0. Make sense? I'm still recording. Okay, so I hope that kind of clears it up. As you go from right to left, it gets smaller and smaller and smaller and smaller, and it'll keep getting smaller, but it'll never actually touch the x-axis. And that is what we call the asymptote, the asymptote, right? Okay, no, don't say it that way. Asymptote, okay? So what is the asymptote? The asymptote is this line. Now, we're not going to call it the x-axis, even though it is the x-axis. We're going to call this asymptote y equals what? It's a horizontal line crossing the y-axis at 0. So that's the asymptote. Ladies and gentlemen, the asymptote is y equals 0. Now, the definition of asymptote is that your graph the exponential growth function that we just did, it infinitely approaches that green line, but it never actually touches. Are you with me? Okay. So we know the asymptote. Now let's also talk about domain and range. So let me write the asymptote down here. Asymptote y equals 0, that green line. What is the y-intercept value? The y-intercept value of your graph. Where does it cross the y-axis? Where does it cross the y-axis, not the x-axis? You plugged in 0, you got out a 1, so the coordinate is 0, 1. So for the y-intercept, it's 0, 1. Okay. Now your domain values are your what? X or y values? X values. So your domain values are your x's. Does this red graph, this exponential growth graph that we just graphed, does it go to the left forever? Yeah. Yes. So this red line or red curve is going to exist at negative 10, right? It's going to exist at negative 15, 20, negative 1,000 if I wanted to, right? It'll infinitely get closer to the x-axis but never actually touch. Now, as I go to the right, it looks like it curves up and that it'll go straight up, but it never actually goes straight up. So let me ask you this. Does the exponential growth function, does it exist at x equals 10? Even though you can't see it? Yeah, it does exist at x. It's going to be way up there somewhere. But I could plug in a 10 right there, and I could do 2 to the 10th power. It'll be a huge number. Make sense? So when you're talking about your domain, you're talking about the x values. To the left, it goes forever, and to the right, even though it curves up, it still does go forever to the right. So what do we say that the domain is? We say that the domain is x equals all real numbers. It goes to the left forever, and it goes to the right forever. And these are the things that we're going to need to understand and be able to do on the next assessment. How about the range values? Now remember, the range values are your y values. So I'm going to put y. Now, it's not y, you got to find out where your y values are at. So let me ask you this. On this red graph, is there any points over here that have negative y values? No. Okay. Where's this red graph at? It all is here and above. So in terms of y as an inequality, y is what? Is it greater than or is it less than a certain value? It is greater than a certain value, right? And what is that value? 0. So your range is y is greater than 0. And that's everything we could explain about this parent graph, the easiest type of graph, y equals 2 to the x power, exponential growth function. So once again, the domain is all real numbers because it goes to the left forever. And even though it curves up, it still continues to go to the right forever, just way up there somewhere. So domain is all real numbers because it goes to the left forever and to the right forever. Now, the range, does it go up forever? Yeah, look, the arrow's going up forever, right? That's not straight up, but nevertheless, it goes up forever. Now, does it go down forever? It stops right there. It'll never go down here. So where's your graph at on your y's? It's greater than 0. You can't even say, if you put this line right here, greater than or equal to 0, it's going to be wrong because it never actually touches 0. So it's just y has to be greater than 0. So before we move on, I do want to explain the shortcut. If you understand that your base is your growth factor, and this is only when you put your inputs in order, -3, -2, -1, 0, 1, 2, 3, like if you were counting. If it's in order, then we're going to be able to use patterns to avoid math. So I did have all these in order, and as you can see, when I plug in 0 right there, 2 to the 0 is 1, and from that point, I already know it's going to grow by 2. So that 1 is going to grow by 2. So 1 times 2 is 2, times 2 is 4, times 2 is 8. So I'm going to be able to get all these coordinates without doing all the math that I did of, 2 to the -1, I move it down, it becomes positive, I end up with 1/2. I don't need to really do that math if I understand that it's growing by this base, which is 2. So only when they're in order, the 1 times 2 will give you 2, times 2 will give you 4, times 2, times 2. And if you go backwards, it'll be dividing by 2. So it'll be easy to come up with all these coordinates if you understand that the base is how your function grows. And that only works when these inputs are in numeric order. Let's move on and try a couple of different ones. So right here, we have y equals negative 2 to the x. And let's actually make an xy table for it. Let's also plug in consecutive integer inputs in order from negative 3 all the way to positive 3. And then it just becomes a question of plugging in your input. Let's go with the easiest input. Which one's the easiest to plug in? 0. Plug in 0 right there, and it'll be 2 to the 0. But remember, this negative is not part of the 2. It's just a negative in front of your answer. So what's 2 to the 0? It's 1, and then with the negative, it's going to be negative 1. Okay? So remember, plug in a 0 right there. It'll be 2 to the 0, which is 1. Anything to the 0 power is 1. And then put a negative right in front of it. That'll be negative 1. So when you plug in a 0, you get out a negative 1. Now, from this point, I could, if I wanted to, I could plug in a 1 right there and get out a negative 2. I could plug in a 2 and get out a negative 4, and so on and so on. Or I could use the base knowing that it's going to grow by 2. So if it grows by 2, negative 1 times 2 is what? Negative 2. And then times 2 is what? Negative 4. Times 2, negative 8. Does that make sense? So you see how easily I got these numbers without actually doing any complicated math? And going backwards, negative 8 to get to negative 4, that's dividing by 2. Dividing by 2, you get negative 2. Dividing by 2, you get negative 1. What's negative 1 divided by 2? Negative 1 half. What's negative half divided by 2? Negative 1 fourth. And then negative 1 eighth if you keep dividing by 2. And you could actually see the same pattern. The numbers 2, 4, and 8 going this way, 2, 4, and 8 are in the denominator. All these beautiful patterns that we could use to avoid doing math. And that's only when your inputs are in numeric order, negative 3, negative 2, negative 1, 0, 1, 2, 3. So let's start graphing 0, negative 1. 0, negative 1 is right here. 0 on the x and negative 1 on the y. And then we go to 1, negative 2. That's right here. We go to 2, negative 4. That's right here. We go to 3, negative 8. That's down here. And if I went to 4, I'd have negative 16. I'd be off the graph, so I'm not even going to graph it. But as I go to the negatives, negative 1 and negative half. So here's the origin. Negative 1 and then negative halfway down would just be between the 0 and the negative 1, right there, halfway down. Let me put a dot right there. That's negative half. And then negative fourth is half of that, closer to the 0. And then negative eighth, closer to 0. Negative 8, or closer, closer, closer. We already know that it infinitely approaches but never touches. So I'm going to draw my graph like if it were actually touching the x-axis, even though it never actually touches. And there's my exponential growth function. Now I know you're thinking, wait a minute, this is not growing. It's going down, but it does grow in a negative direction. Now you're thinking, wait, that's impossible. There's no such thing as growing in a negative direction. It is possible. If you guys get a credit card and you have a 0 balance, you'd be right here, and then you start using it, it just grows in a negative direction, right? Your debt grows. Anyway, so I want you to compare the original one that we did up here, that red one, compared to this guy. What happened? What happened to the actual original graph? Instead of going up, it goes down from left to right. That negative sign in the front, what it does, it makes your graph that was going up, it makes it reflect and go down. It reflects on the x-axis. That's more for Algebra 2. Let's graph the other one. Oh yeah, by the way, what's the domain of that blue one? X equals all real numbers. So on these growth functions, x is always going to equal all real numbers, because it does go to the left forever and it goes to the right forever. Okay? So the range, how about the range? Y. Exactly. There is nothing up here in the y's being positive. This whole graph is down here where the y's are negative. So we know it never actually touches 0. It's just less than 0. So we say y is less than 0. That is your range. Now if I did ask you for the asymptote, I'll just stop, I'll abbreviate. The asymptote would be y equals 0. So the asymptote would be this red line, y equals 0. It never actually touches, just infinitely approaches it. So let's do the same for this guy over here. I want to do this one in red. plug in consecutive integer inputs. And if you did plug in a 0 right here, you'd have 2 to the 0. What's 2 to the 0? 1. And then 1 times half. What is 1 times half? 1 half. So when you plug in 0, you get out a half. Now, I could continue and plug in 1 right there. Might as well, why not? What's 2 to the 1? 2, and then 2 times half? What's 2 times half? 1. So when I plug in a 1, I get out a 1. But you see, I didn't even have to think about that math. If I know that the base is 2, I know that the growth factor is 2, which means that half, it's going to grow by multiplying by 2. What's half times 2? 1. What's the next one going to be if it's growing by 2? Then this is going to be 2, and then 4, and then 8. Exactly. So 2, 4, 4, 8. You could easily come up with all these numbers without doing any math because of the pattern that we know exists, because of the growth factor. Now, if it's growing by 2 this way, going backwards would be dividing by 2, right? 8 divided by 2 is 4, divided by 2 is 2, divided by 2 is 1, divided by 2 is half. What's half divided by 2? 1/4, and then 1/8, and then 1/16, and then 1 over 32. We know that it infinitely gets smaller. Are you with me? No, because there is no negative in this part of the function. Even though it's negative, all it does is makes it move down to the denominator, which creates it to be a fraction. Okay. So anyways, let's graph this in red. The first coordinate, actually let me do it in black. The first coordinate is 0, half. So 0 and then halfway up is right there. Then the next coordinate 1, 1 is right there. The next coordinate 2, 2 is right there. The next one 3, 4 is right there. The next one 4, 8 is all the way up there. And going in the other direction, it's going half, half, half. So it approaches the same asymptote. So there's my exponential growth function. It is trippy. And of course, we could answer, what is the domain of that black exponential graph? X equals all real numbers. What is the range of that black exponential graph? Y is greater than 0. Right? So the blue one was y is less than 0 because it's below the y value of 0. The black one is y, the range is y is greater than 0 because it's above the y value of 0. So I think I'm going to pause right there and I'm going to start up another video on the next section. Or not on the next section, on the next part of this worksheet.